Hello everyone. Today I'm going to talk about a rather recent paper of mine, which is titled Filter Simplicial Homology, Graph Dissimilarity and Überhomology. So let's start with a brief overview. Okay, so first of all, X for us is always going to be a finite and connected simplicial complex whose vertices are V1 through Vm, and we'll always assume that these vertices are ordered somehow. Okay, so the main idea here is to fix a bi-coloring of the vertices of X. So this is this epsilon here is a coloring in either white or black or 0 or 1 of these m vertices of X. And of course, the set of all possible colorings here is isomorphic to Z2 to the nth power. Okay, now that we have this bicolored simplicial complex, we can use it to define two different homologies that sort of mimic the behavior of the usual simplicial homology of X. And these are called the horizontal and diagonal homology respectively. And their difference is in how they behave with respect to the coloring. So first of all, we'll see how these homologies actually generalize the usual simplicial homology we are all used to. Also, we'll show how and why they are connected to discrete Morse matchings on X. And then we'll show some applications of these homologies to graph theory. In particular, we'll use them to define a new notion of graph dissimilarity, and also to construct a related graph invariant, which is conjecturally complete. Then we'll get to the Überhomology. So we'll see basically what happens when you consider all possible colorings at once. We can organize these colorings in a sort of poset diagram, which is reminiscent of Kovanov's cube of resolutions for his link homology. And we can create a new homology by considering this sort of cube decorated with all the horizontal homologies of corresponding to the given bicolorings. I'll say more precisely what I mean in just a bit. So it turns out that this homology, which is called Überhomology, is indeed a triply graded homology. So it has a homological grading, decreasing by 1 under the action of some differential. But also it has another grading. One it is induced by the dimension of the simplices, while the other is induced somehow from the coloring. So the first striking difference with any other homology theory, for simplicial complexes is that this Überhomology is not a homotopy invariant, but possibly even better, it encodes some weird property of the simplicial complex. In particular, we'll see that, for example, in its lowest degree, it encodes some purely combinatorial information about X, while in its top degree, which is going to be m, so the number of vertices, it, for at least in the case of simplicial complexes whose geometric realization is the triangulation of some, let's say, closed manifold, it recovers the fundamental classes, so purely topological information about X. Okay, let's start by giving some notation we'll use throughout. First of all, here, C of X is just going to be the usual simplicial chain complex of the simplicial complex X. So it's basically the graded abelian group spanned by the simplices of X. And delta is going to be the simplicial boundary. So this is just the sum over all codimension 1 faces for each of the simplices in X. And I said sum because I'll always be using throughout just F2 coefficients, so we don't have to worry about signs and all that. Okay, so if we have a bicoloring epsilon of a simplicial complex X, we can take any simplex in X and define its epsilon weight or coloring weight. This is just going to be this W epsilon of sigma, and this is just the number of white vertices inside of sigma. Note that I'm not defining this weight for the whole simplicial complex, rather we do it for each simplex separately. And this will be important in just a few minutes. Okay, let's see an easy example here. We have the tree simplex with this coloring epsilon, which is 0, 1, 1, 0. So the 1 and 4 vertices get a white coloring, while the 2 and 3 vertices get a black coloring. So the epsilon weight of the whole thing is going to be 2, with respect, of course, to this epsilon. While, for example, if we take the two simplexes spanned by 1, 2, 3, this will have a weight of 1, the edge 2, 3 will have a weight of 0, and so on. Okay, so just by defining these colorings, we get for free basically a splitting of the simplicial differential into two components. The first one is called horizontal, and the second one is called diagonal components. And we'll see in a moment why this name. So, roughly speaking, the horizontal component preserves the epsilon weight. So basically, on a given bicolored simplex, its horizontal boundary is going to be the sum over all the faces that are obtained from the simplex by removing exactly one black vertex. Or in other words, the horizontal boundary is the sum over all faces that have the same number of white vertices as the initial simplex. While for the diagonal differential, we have the opposite behavior. So inverting the two colors. So we can also define this complex here, Ci of x, depending on the coloring epsilon, in coloring degree k. So this is just going to be the span over all simplices sigma inside x of dimension precisely I, and whose epsilon weight is precisely k. So in some sense we are taking the underlying module of the simplicial chain complex of x, and we are giving a bigrading to all of its elements. Basically, we're passing from a one-dimensional thing to a two-dimensional thing. We'll see in just a second one example though. And finally, we can sort of take all of these subcomplexes all together as a direct sum, indexed by I, which is the dimension of the simplices, which goes, of course, from 0 to the dimension of the simplicial complex, which is just defined as the maximal dimension of the simplices inside it, while the coloring degree k will go from 0 to the dimension of x plus 1, since n simplex will have at most n plus 1 white or black vertices. Okay, now the first nice thing here is that both these components taken separately do actually square to 0. And we can see it, for example, for the horizontal boundary, which is the one that we'll use throughout. Why this is true? So we can do this for one simplex at a time. If the simplex does not contain at least 2 black vertices, then the square of the horizontal boundary is automatically 0, since recall that it needs to preserve the number of white vertices. So if or even better, that the horizontal one is obtained by removing black vertices. So if there are less than 2, you cannot remove 2. Okay, so if instead there are 2 or more black vertices inside a simplex, then the square of the horizontal differential is just given by all the dimension 2 faces of the simplex obtained by removing 2 black vertices. But this can be done, of course, in two different ways, choosing first one black vertex and then the other, or in the other way around. And so these two choices cancel out over f2. Hence the square differential is actually 0. Then we can use this to define these two homologies called horizontal and diagonal homologies of the bicolored simplicial complex x epsilon. And well, this is the notation. The H here stands for horizontal and diagonal here. And let's see an explicit example. Here we have a bicolored 2 simplex. The coloring here is 1, 0, 0, so we have V1 in black and V2 and V3 in white. And here on the right you can see this two-dimensional representation of the simplicial J complex for X. Here you can see the face F, which is in by degree 2, 2, meaning that it's of course it's a simplex of dimension 2, and also it has 2 white vertices here, and the same for all other elements inside X here. Basically, as I told before, you can see that this is sort of a two-dimensional development of the one-dimensional simplicial chain complex for the 2 simplex in this case. Now, recall that the horizontal boundary was given by the components of the simplicial boundary that do preserve this weight degree. So in particular, we can obtain the horizontal complex from this one in the top right by just deleting all the diagonal arrows. So we get this complex here in the lower left, and all of these components here are acyclic. They do not contribute to the homology. So the homology is just generated by V1, generated by this V1 in by degree 0, 0. And let's see. So for example, this differential here between F and E2 is just this here, since E2 is the only face with the same number of white vertices as F. While of course we can obtain the diagonal homology in the dual way by just deleting all the horizontal arrows. And in this case we have a square here, but the square again is acyclic, so the homology is generated in this case by either V2 or V3 in by degree 0, 1. So we see that the two homologies are different. Now I also want to note that in this chain complex here on the top right is indeed a filtered chain complex, since all the arrows, all the differential can do are either to preserve the filtration degree, this coloring degree, or lower it by 1. And this depends on whether the arrow belongs to the horizontal or diagonal complexes. Okay, there is a easy form of duality relating these two homologies. So the horizontal homology of a bicolored simplicial complex X is canonically isomorphic to the diagonal homology of X with the opposite coloring. So this is the coloring that assigns black to white and white to black. So it's like the real opposite of epsilon. So we can, from now on, we'll just discard the diagonal homology and work only with the horizontal one for simplicity. Okay, so as I stated at the beginning, these homology do actually generalize the usual simplicial homology and complexes for X. In particular, let's see what happens for the all-white coloring. In this case, it's not so hard to see that there are no horizontal differentials, so that the homology actually coincides with the horizontal complex. And why are there no differentials? Because there are no black vertex that you can pick out to obtain faces with the same number of white vertices by default. So in this case, the homology coincides with the complex, and the horizontal complex with the all zero coloring coincides with the chain complex, the simplicial chain complex for X, but with a little difference. So in this case, this is a bigraded complex, while this part here is just singly graded, and we need to input the number of white vertices in each simplex, and this is clearly k plus 1 for a k simplex. So in particular, we obtain basically a complex which is diagonal and has no differential. In particular, if we forget in this term on the right the filtration, we just get the usual the filtration degree or the coloring degree. Alternatively, we get the usual simplicial chain complex for X. On the other side, instead, if we get the all one or all black coloring, we just get the standard simplicial homology of X. And this is because, if all vertices are colored in black, then the horizontal boundary coincides with the usual simplicial boundary, and there is no filtration here, basically, or more properly, all the filtration is concentrated in degree 0. And so basically you get just a one-dimensional complex, whose homology is precisely the homology of X. Okay, let's change a bit the subject, apparently. And let me talk a bit about Morse matchings and the relation to this horizontal homology. So I'll link another video in which I talk in more detail about Morse matchings. So here I'll just give a really short introduction. But anyway, if you have a simplicial complex, ignore the bi-coloring here for now. In this case, the two simplex. You can look at its phase poset, which is just basically an oriented graph whose vertices are the simplices inside X, and arrows are represent phase inclusion and are oriented in the direction of decreasing dimension. So here, again, ignoring the coloring for the red arrows here, for a moment, you can see that this is the phase poset corresponding to these two simplex. Okay, and now we can look at matchings on this phase poset, and matchings in general for a graph are just a collection of edges that do not share any vertex. So in this case, these red arrows here form a matching on this phase poset, and we say that this is a matching supported on the simplicial complex X. There's also a little game we can play. We can invert the orientation of all the arrows that belong, all the edges that belong to a matching, and this gives us a new directed graph. And now, if there are no oriented cycle in this graph, as happens, for example, for this case here, we say that the matching is a discrete Morse matching, or is an acyclic matching. And this terminology is no mistake, so these discrete Morse matchings are in fact related to discrete Morse functions, as introduced by Foreman in the 90s. And these discrete Morse functions are, of course, a discrete analog of smooth Morse functions on manifolds in general. In particular, discrete Morse matchings can be thought of as being a discrete analog of the gradient flow of a Morse function on a given manifold. Okay, so we know now what discrete Morse matching is, more or less. Now let me introduce these elementary colorings. These are really simple, or just a coloring, the bi-colourings of a simplicial complex, in which we are only coloring in black a single vertex, like this. Now, this given bi-colored simplicial complex, we can sort of encode the information about the coloring in the phase poset through this Ix epsilon. So these are subgraphs of the phase poset whose only edges are those given by the horizontal boundaries in the horizontal complex. What do I mean by this? So first of all, note that the phase poset of a simplicial complex can be thought of as being a graphical representation of its simplicial chain complex. So what I mean by this, that the boundary of 0, 1, 2 of the whole thing is given by 0, 1, 1, 2, and 0, 2, and the boundary of 0, 1 is 1 and 0, of course. So if you take sort of the homology of this poset, you recover the simplicial homology of X. Now, we can only consider the edges that correspond to components of the horizontal boundary inside this bi-colored simplicial complex. So in the case at hand, let's see, the whole two simplex 0, 1, 2 will have horizontal boundary consisting only of 0, 1, because this has only two white vertices. The same holds for 1, 2, and 1. Let's see, 1, 2, its horizontal boundary is going to be only 1, and 0, 2, and 0. So the only unpaired vertex here, which is also called a critical cell of this discrete Morse matching, is 2, which is the only black vertex here. Okay, last definition before we get to some actual result. We say that a bi-coloring of a simplicial complex is Dalmatian if it's, first of all, different from the all-white coloring. We need some black vertex. And if it satisfies this weird condition. So what does this mean? It means that if you take any pair of simplices inside X, then if these two simplices intersect, then their intersection, the vertices in their intersection, can contain at most one black vertex. And here in the top right, you can see a sort of, well, it's a triangulation of the two sphere, in which we see a Dalmatian coloring. So this condition here can also be rephrased in terms of the stars of the black vertices, and what we want basically is that the stars of two black vertices do not intersect, or their closure better do not intersect. So this is an example of Dalmatian coloring. Okay, so the first result I want to talk about is the connection between discrete Morse matchings and these subgraphs, and in turn with the horizontal homology I just described. So these subgraphs provide us with discrete Morse matchings on the phase poset for X, if and only if the coloring is Dalmatian. So in the example before, just this really trivial example, there's only one black vertex, so of course this is a Dalmatian coloring, and you can see indeed that these red arrows, as we've seen before, do give us discrete Morse matching on this phase poset, meaning that there are no, if we reverse the orientation of all the red arrows, we do not get any oriented cycle inside it. And as a consequence, if we have a Dalmatian bicolored simplicial complex, then the generators of the horizontal homology are in bijection with the critical cells of the Morse matching induced by this subgraph. And yeah, as I mentioned before, critical cells are just the unpaired vertices inside a phase poset. Okay, so one might wonder, how do these subgraphs change when we change the coloring? Is there any relation among them? And or alternatively, how does the horizontal chain complex change when we change the coloring? And here we have well, for me, quite surprising and really simple answer to this. So if we have a general bicolored simplicial complex X, its induced subgraph in the phase poset with respect to the coloring epsilon is just going to be the disjoint union of all epsilon elementary colorings that are contained inside epsilon. So we can split epsilon into its components, so each of the vertices that are colored with 1, and each of these will give us an elementary coloring. And well, we can see here with an example what I mean. If we take the tree simplex 1, 2, 3, 4, then if we color only 4 in black, we get this orange induced subgraph, which corresponds to the components of the horizontal boundary of that complex. While if we color in black only 3, we get the purplish subgraph. But the neat thing is that if we color both 3 and 4, the subgraph that we get, or alternatively the horizontal differential that we get, is just a disjoint union of the of the orange and purple colorings, well, edges here. And by this joint union here, I just mean that the edges are all different, but they can share endpoints, unlike what happens for matchings, of course. So in particular, another consequence of this is that given any simplicial complex, using this sort of procedure, we get a partition of its simplicial boundary into disjoint components that are all discrete Morse matchings on the phase posets, which I think it's kind of nice. Probably known already somehow, but I don't think using this point of view. So now let's dive into another slightly different topic here, and let me start from the picture. So this picture on the left, we can start from a knot diagram or a link diagram on the two-sphere. Forget about the information over and under, so we're just looking at the knot projection, and then color in a checkerboard fashion in black and white all the regions that are in the complement of this projection of a knot or a link. And this will give us a graph which is called the black graph, whose vertices are all the black regions and edges are given by crossings. But of course, inverting the role of the colors, we also get a white graph, which is this one here, whose of course vertices are white faces and edges again are crossings. What we can do then is we can superimpose on the two-sphere these two graphs, and this gives us what is known as the unbalanced Tait graph, whose vertices are either coming from black regions, from white regions, or from crossings. And these gray vertices in figure are just given by the intersection of two dual edges, one in G and one in G star. Okay, then once we can do this other construction here, given a knot projection, we can consider its Tait graph, which is superimposed to the projection here, and then we can consider only the let's say part that in this case is the subgraph given by the white regions and the crossings. So in this case, these green vertices here. And well, first of all, note that there is one vertex at infinity, which is the white region at the in the outer. It's the outer region with respect to this diagram, and that this graph that we obtain can be identified with the first barycentric subdivision of the white graph of this diagram here. And then we can look at matchings inside this graph. These are these two pink edges, for example, and then we can look at the dual, which is in this case the blue graph, or it's barycentric subdivision, and take the complement of this matching. So what is the complement of a matching here? Note that the edges here correspond to half edges inside this white graph, which of course is in reddish here in figure. And so if we match a half edge here, we want to remove from the blue graph here this edge, which is dual to the half edge that is matched here. So you can see here we have to remove this edge in the blue or black graph, and this other edge, because this and this half edges here are matched. So this is, if the matching was called M, this is a G of M. So what is written here is that if we get for any matching inside a barycentric subdivision of the dual graph of a plane graph, we can define this complementary subgraph in the starting plane graph that we had with respect to this matching. Okay, also we do have a really simple bi-coloring on induced on the matching complex of the Tait graph of a given graph G. So if we have a given graph G, we can consider its Tait graph like this, and we can consider its matching complex, which I haven't defined. This is just the simplicial complex whose vertices are the edges inside, in this case, the Tait graph for G, and whose simplices are given by matchings. So disjoint collection of edges inside this Tait graph. And the obvious coloring that we're considering here is induced by the colorings of G and G star, so in white and black respectively. For this, note that each, let's say, black vertex here will be connected only to gray vertices, while all the whites will be connected again only to gray vertices. So any edge will contain exactly one gray and one either white or black vertex, and we'll say that the corresponding vertex inside the matching complex will be colored in black or white, depending on the color of the unique black or white vertex inside the half edge here. Okay, this was a mouthful. Let me just continue for a bit with this. So we have, we can look at the filtered chain complex of the simplicial homology for the matching complex, and we'll see that in the 0th degree we will have a subcomplex which can be identified canonically with the matching complex of the first barycentric subdivision of the graph G we started with, since all of the vertices here will have only will be all black, and therefore in the 0th degree of the filtration here of the horizontal homology we get only black what were black half edges in the Tait graph. So we get this object here, while if we get if we look at the homology for filtration level sufficiently high, we get the matching complex of the whole thing. So in some sense these two simplicial complexes are the opposite sides of this filtration. Another way of saying this is that in this the homology of this matching complex of the barycentric subdivision is in the degree 0 of the associated graded object to this filtered chain complex. Okay, and then we can state this result that basically just tells us that in the case of plane graphs and this construction of the Tait graph, we can actually describe explicitly the horizontal homology of the matching complex in terms of simple pieces somehow. So let's look at the horizontal homology of the matching complex of the Tait graph for a given plane graph G. With the coloring, of course, induced by the colorings of G and G star. Then we have a graded isomorphism of the horizontal homology of this matching complex in degree K, and this sum, where these summands on the left are the reduced homology of all the matching complexes of the barycentric subdivision of the complements of the matchings on the dual graph, if these graphs are non-trivial. And yeah, I forgot to say the matchings that we're considering in the dual need to have precisely k vertices to give us this coloring degree k. While the second summand here is given instead by all the matchings in the dual that are in some sense spanning, so they leave no edge in G untouched. And here, for each of these, we just get a copy of f in this by degree. And this, of course, holds only for k greater than 0. When k instead is equal to 0, follows from what we said before, that the homology of the matching complex of the Tait graph with this by coloring in coloring degree 0 is just the homology of the matching complex of the barycentric subdivision of G. Okay. We can now move to a slightly different application of the horizontal homology, and this will be, we'll use it to construct a dissimilarity function for graphs. So let's consider the case where the simplicial complex X is a graph, which of course will be a simple graph, meaning that between a pair of vertices you can have at most one edge and there are no self loops. Then, given let's say a connected and epsilon colored graph, G epsilon, we can encode in a sequence of 4 tuples the ranks and bigradings of the horizontal homology of the graph. More precisely what I mean, we can fix a level J between 0 and the number of vertices inside the graph, and for each of these J we look at this theta sequence, which is the 4 tuple JIKR, where J is just this J here, I is the dimension of the simplices, K is equal to the coloring degree, and R is equal to the rank in the case where the rank of this homology group, this horizontal homology group, is greater than 0. Okay, so these 4 tuples, or we'll see an example of what I mean in just a second. I haven't been super clear here. So these tuples are orders simply by lexicographic ordering. So the ones with lower j are before, and so on. And this sequence can be thought of as being, well, as giving some approximation, what are called feature-based information on G, ranging from a local kind to a more global kind. And what do I mean by this? Is this. So if we take two graphs G1 and G2 with the same number of vertices, then the theta sequences of G1 and G2 in degree 0 will coincide if and only if these two graphs have the same number of edges. Then assuming that they coincide in degree 0, we can look at degree 1. Here the two theta sequences for G1 and G2 will be the same if and only if the two degree sequences of the graphs are the same, and the degree sequence is just the set of all possible valences of vertices inside G1 and G2 respectively. On the other end of the spectrum, if we take the theta sequences of let's say maximal level in degree given by the number of vertices of G1 and G2, then these the theta sequences here will coincide if and only if these two graphs have the same homology. And since we were talking about connected graphs, we are just looking at H1. Okay, now how can we use this to construct a dissimilarity function? But more importantly, what is a dissimilarity function? So a dissimilarity function is just a function that takes as input two graphs and spits out a number, let's say between 0 and 1, telling us how similar these two, or well, in this case, dissimilar these two graphs look. Now we can define this delta of G1, G2 for a pair of simple and connected graphs with the same number of vertices as 1 minus 1 over m times the minimum level j, such that the theta invariants do not coincide. So as a stupid example, if the two graphs have a different number of edges, then this minimum will be 0 and the dissimilarity is 1. And yeah, of course, the highest the level in which the two theta sequences start not to coincide anymore, the lower the dissimilarity will be. Particular, yeah, we can connect, we can give some bounds, lower bounds on the dissimilarity in terms of some intrinsic data on the graph. So here we can give a lower bound in terms of the girth of these of the two graphs. Sorry, here it should be a G2 and G2, and in terms of the vertex cover number of the graphs. Well, the girth is just the length of the shortest loop inside the graph, and the vertex cover number is just the minimal number of vertices inside the graph that cover all the graph, so such that all the edges have at least one of these vertices intersect at least one of these vertices. Let's see a concrete example to explain a bit what I'm talking about. So let's consider these two graphs on 6 vertices, G1 and G2. And let's note immediately that they have the same number of edges, and their degree sequences are the same. These are 3 regular graphs. So the valence of each vertex here is 3. So in particular, from what I said before, the theta invariants in level at least 1 will coincide. So we can compute the horizontal homologies of G1 and G2 in level equal to 2, which just means that we will color in black exactly 2 vertices inside these graphs and look at all possible horizontal homologies with these colorings, and then collect the ranks and gradings of all the elements inside these homologies into these theta invariants. So here, for the first graph, we get this homology, so of rank 4 in by degree 1, 2, and so on, in 6 possible cases, this in 6 possible cases, and this in 3 cases. While for the other graph, we get these 2 other different homologies. So already from this, you can see that the 2 theta invariants will not coincide in level 2, and therefore the dissimilarity of these 2 graphs is 1 minus 2 over 6, so 2/3, where 6 being the number of vertices. Okay. I said before that the vertex cover number gives us a bound on the dissimilarity between 2 graphs, but in fact more is true. We can look at all possible vertex covers of a given graph G, and these are in fact in bijection with the bi-colourings of the graph, such that the horizontal homology in coloring degree 2 equals 0. So, since finding vertex covers of a graph is a really, really hard problem, by hard I mean NP-complete problem, this tells us that computing these horizontal homologies in general is not going to be really easy, even though it's possible to write programs that compute these groups that are quite efficient. Another remark is that this dissimilarity function can differentiate between quite similar graphs. And what do I mean by similar? I mean graphs that have the same spectrum, for example, for the Laplacian, for the adjacency matrices. So this delta does not seem to care about some of the most, let's say, classical information about a graph. It looks at sort of different things. And easy to verify fact is that indeed this delta provides us with a pseudometric on the space of graphs, let's say, with the same number of vertices. And a pseudometric is just a metric where you're removing the condition that it needs to be 0 only for an element and itself. So, or better saying that if delta of xy is equal to 0, then x equals to y. And I conjecture that this delta is indeed a metric on the space of graphs with the same number of vertices, and which is equivalent to saying that the theta sequence invariants are in fact a complete invariance of graphs. So I'm not really convinced that this conjecture is true. However, I've looked a lot, and we'll see in a minute what I mean by that, for counterexamples, and I couldn't find any. And also I think that studying more these theta invariants could be interesting on its own right. And in particular, there seem to be quite a few connections with known algorithms to, if not resolve, to give some partial solution to the graph isomorphism algorithm. And I'd be curious to know a bit more about that. So let's talk about the effectiveness of this dissimilarity measure. I wrote a code in Python, or more precisely in Sage, to compute the, let's say, probability that two given random graphs on a given number of vertices have a dissimilarity more than a certain threshold. So, for example, here we're looking in this table at trees between 11 and 16 vertices, and here is the number of such trees. So we start from 235 on 11 vertices to 19,320 on 16 vertices. And this number here is the probability that two randomly chosen graphs inside here have dissimilarity or have their theta sequence invariants that are different up to this degree here. And as you can see, the probabilities get really, really small when we move up into the coloring levels. Even more, I looked also at all possible graphs with up to 9 or 10 vertices, and you can see, well, how the number of such graphs, connected graphs, actually increases by a lot, and how the actual probability that we have rather high dissimilarity decreases by a lot as well. So these computations were quite slow on the first draft of my program, but there are a few ways in which one can speed up these computations by looking at symmetry and so on. So it's these programs are on my GitHub, and I think I'll update them soon with some better version. Okay, let's get to the final part of this talk. This concerns the Überhomology. And as I mentioned in the introduction, this is basically just a way of organizing all possible horizontal homologies into a poset and use them to compute a further homology theory for simplicial complexes. More concretely, if we have a simplicial complex X on m vertices, then we get naturally that the colorings form a poset, which is basically just a cube. This is called a Boolean poset. And so in which 0, 0, 0 is the first coloring, then 1, 0, 0, 0, 1, 0, and so on, until we get at the on the right here at the all one coloring here. And we can decorate each of the vertices of this cube with the corresponding horizontal homologies with respect to that given coloring. And what we'll do in just a second is that we'll associate to each of the edges here a map between the horizontal homologies, which in turn will give us a differential. And this is precisely the same construction used by Kovanov for his link homology, as then reinterpreted by Barnatan in his really nice paper. Okay. We can. What is left to do here is to define these maps on corresponding to the edges of a given to the edges between two colorings or two horizontal homologies in the poset, in the cube poset that we just saw. So this eta will connect epsilon, the coloring epsilon, to epsilon prime, meaning that epsilon prime is obtained by coloring exactly one white vertex inside epsilon in black. And this map here is just going to be it's going to be just induced by the identity map. And what do I mean by that? The identity map between the filtered chain complex of the bicolored simplicial complex X and X with the coloring epsilon prime is a filtered map, meaning that the image to the identity of any given simplex will either have the same number of white and black vertices, and so it will have the same filtration level, or it will be decreased by 1. Then this map eta associated to the edge eta is just the map induced on the horizontal homology by the grading preserving part of the identity maps seen as filtered maps. With this definition in hand, we can then just define for let's say homological degree j between 0 and m these Uber complexes of X, which are just going to be the sum over all the horizontal homologies whose weight of the coloring is precisely j, and by this I mean just the number of white vertices inside this is the number of zeros inside the string epsilon, seen as the string inside to the m. In other words, this will be the 0 Uber complex. This column here with exactly one black vertex is going to be the first complex, the second, and the third. And in the same way, we can construct these differentials, which are going to be just the sum over all maps starting from the jth complex and going to the j plus 1 of these maps associated to the edges. Now, it's not too hard to prove that with the definition I just gave, this is indeed a chain complex, and we can take its homology, which is called the Überhomology, which is denoted this way. So this is a triple sum for j, which is the homological degree, going between 0 and the number of vertices inside the simplicial complex X. I is just going to be the another grading, which is the dimension of the simplices, in analogy to the horizontal homologies before, and this is going to be denoted here. And k is just the number of white vertices inside simplices. Precisely. So these two extra grading. First of all, it's not hard to see that are preserved by the differential, while the j1 decreases by 1. And these are induced by the internal gradings inside the horizontal homologies. Let's see actually a concrete example here. We have a really simple simplicial complex, which is the one simplex E with vertices v1 and v2. And here we have the sort of poset structure for the coloring. So we have 2 white here, 1 white and 1 black on this level, and 2 black here. And here are the maps associated to the edges. Well, here on the right we have the same poset, just decorated with the corresponding horizontal homologies. So in coloring degree 0, 0, in the bi-coloring 0, 0, we will have just the simplicial chain complex for the one simplex put along this diagonal. So we'll have E in by degree 1, 2, since it has dimension 1 and has 2 white vertices, and then V1 and V2 in by degree 0, 1. So the homology in this first part, it will be generated by everything, since there are no differentials in the old white coloring. So E will generate non-trivial sum of the homology in by degree 1, 2, and so on for these others. While if we take the colorings in this level, then E and V2 and respectively E and V1 will form cyclic pairs, and the two horizontal homologies will be generated in by degree 0, 0 by V1 here on the left and V2 here on the right. While here at the end we have that the whole homology, of course, as I said before, is concentrated in filtration degree 0, and so this chain complex will coincide with the usual simplicial chain complex of the one simplex, whose homology is generated by degree 0, 0 by either V1 or V2. So how do we compute the Überhomology of this? Well, first of all, let's note that both these two arrows are the zero map, since V1 in the case here on the right becomes a cyclic here, so it's since here we have the horizontal homology and here we have the horizontal homology, this gets V1 gets sent to 0, while V2 is not would not be sent automatically to 0 because V2 is non-trivial here in homology. However, note that the filtration degree here is 1 and here is 0, and by definition this map only considers the graded part of the identity maps. So this map is 0, this map is 0, and all the non-trivial cycles, so all these guys here in the horizontal homology, are also non-trivial in the Überhomology. While here these two maps send V1 into V1 and V2 into V2, but these two are homologous here in this complex, so the sum of V1 here and V2 here give us a non-trivial cycle in homology. And of course here there's no homology left because V1 or V2 are in the image of these two maps. So summing all up, we have in the Überhomology in degree 0 is given by spanned by E and V1 and V2, and in degree 1 is spanned by V1 plus V2. And it's possible to actually compute the Überhomology of all the simplices and of all their boundaries, and we'll see some computation in other specific cases in just a minute. Okay, let me give the first result on this Überhomology. Okay, so if we have connected simplicial complex X, whose vertices are V1 through Vm, then we can give a completely intrinsic interpretation of the Überhomology in degree 0. So if we have more homology in degree 0 and in dimension I, this will be just spanned by this factor here, where Ni is just the number of I-dimensional simplices inside the intersection of the closure of all the stars of the vertices inside X. What do I mean by this? We look at the closure of the star of each vertex inside X, and we look at the intersection of all of these sort of balls inside our simplicial complex. If this intersection is non-trivial, then the H0 is non-trivial, and furthermore, the dimension of the simplices inside this intersection will give us these exponents, and these by creating here the number and dimension. Let's see here, the closure of the star V1 and V2 are the whole thing, and in fact here we see that E and V1 and V2, so everything is non-trivial in the 0 degree of the Überhomology. Particular, we have this really immediate corollary. The H0 of the barycentric subdivision of a simplicial complex will be always trivial unless the simplicial complex we started with was simplex. In that case, the Überhomology in degree 0 is generated as rank 1, and it's generated by the barycenter at the center of the simplex. This follows immediately by noting that the closure of the stars in the barycentric subdivision of a simplicial complex intersect non-trivially, if and only if we are in the case of the simplex. And another way of looking at this is that if we have a simplicial complex with diameter greater or equal than 3, then the Überhomology in degree 0 must vanish, of course, for the same reason, because the stars, there will be at least 2 vertices whose star cannot intersect. Now let's see what happens on the opposite side of degrading. So if we have, for example, if X is a triangulation of a closed manifold with m vertices, and let's say a n manifold for concreteness, then the Überhomology in its top degrees, or m here, actually does coincide with the fundamental class of the manifold, which is kind of nice, since we just saw that in degree 0 of the Überhomology we get something which is purely combinatorial, so just intersection of balls. This is non-topological at all. Well, here we get something which is a topological invariant. It's invariant under homotopies of our manifold. And so this is somehow reminiscent of Czech's cohomology. And I think that that point of view should be looked into. And also then we can look at the behavior of the Überhomology in these extremal degrees under the operation of coning and suspension. So again, if X is any simplicial complex with m vertices, let's say connected to be safe, then the cone will have n plus 1 vertices, and we can look at its extremal degree, and the Überhomology in this top degree of the cone will always be trivial, while the Überhomology of the cone in its lowest degree, so 0, it's going to be just the cone of the Überhomology in degree 0 of X, and I'll explain in just a second what I mean, or of rank 1 and generated by the cone point if the Überhomology was trivial to start with. So what I mean by this, the Überhomology here in X will be spanned by, will be generated by a bunch of simplices, and then we just take the cone of those, the cone of those simplices will generate the Überhomology in degree 0 there. For suspension instead, the Überhomology in degree 0 is unchanged, so it's the same as the Überhomology of the initial simplicial complex. And in the case where, again, X is, for example, a triangulation of a closed manifold, then the Überhomology in the top degree for the suspension, so m plus 2, coincides with the Überhomology in degree m, which again, from this result we know is the fundamental class of X, only we have this slight shift of in the degree here. Okay, finally, the last topic I'm going to talk about is that we can use the Überhomology to, or even better, we can specialize the Überhomology to find some new homology theory for graphs. This is because the Überhomology has this triple degree, with one degree being the homological one, while the other two, so dimension of simplices and number of colors, the number of zero-colored vertices, are preserved under the differential of the Überhomology. Therefore, if we fix a by degree for a given simplicial complex, we obtain from the Überhomology a singly graded theory, which is just the Überhomology in that by degree, letting the homological degree vary. In particular, if our simplicial complex was a graph, then we can obtain 4 priori we could obtain 6 homology theories. It turns out that there are only 4 that are interesting, and in particular today I'm going to talk about a special one, this bold H0 of G. And here I said 6 because for a one-dimensional simplicial complex, of course the dimension of the simplices is at most 1, so we have 0 and 1. And then the number of white vertices can be 0, 1, or 2. So we have 6 possibilities for these by degrees. So this H0 of G is going to correspond to the by degree 0, 0. And well, I give first of all an alternative description for it, and then we'll see some computations. So if we have epsilon colored graph G, we can define its black subgraph as the subgraph spanned by black vertices, meaning that if you have 2 black vertices and an edge between them, then the edge will belong to the black subgraph. And to each, then we can consider as before like the poset of all the possible colorings for a given graph, and we associate to the edges eta the maps that are induced by the inclusion of the connected components of the respective black graphs. I'll show with an example what I mean just in a second, but suffice to say that we can construct just as before a chain complex whose elements here are the span over F of the connected components of the black graph induced by a given coloring, and well, the differentials are given by the sum of all of these maps induced by inclusion. And note that if we add a black vertex, then the connected components can either merge between them, or stay the same, or get bigger or increase in number. It's there are many possible things that can happen in general. And here we can see in a really simple example, so a line graph of length 2. Here on the left we have this the poset here of colorings. You can see here on the left that there are no black dots. Here all 1 black dots, here 2, and here 3. And here on the right we are looking at the same poset, only recording the black subgraphs and their connected components. So here, well, on the left we have nothing because we have no black vertex. Here we have only the first one in black, second and third. Here we have a connected component which is given by 1, 2, and here we have 2 connected components. One is 1 and one is 3. While here we have 2, 3, and here of course we have the whole thing. And so this just looking at this black connected components gives us a chain complex by summing over all edges here, and the homology of this chain complex is precisely the H0 that I was talking about. And this can be obtained as the Überhomology in a specific by degree. Now, there are a few things that we can say about this homology. First of all, if we start with the complete graph on n vertices, then the H0 is generated as rank 1 and is generated in degree 1 by the sum of all the subgraphs that are sort of degenerate, consist in only 1 black vertex. And also, a thing that I found quite surprising at first is that this H0, again, just as similar to the horizontal homology, is sort of good at distinguishing graphs that look similar from many other points of view. So, for example, from the spectral point of view. And I wrote another program to compute this knot homology. And here are some computations for the cube graph, which is the one skeleton of the n-dimensional cube. you can see that the sort of ranks and degrees seem to obey a pattern, while here are some computations for the grid graph. This is just a graph given by a n by m rectangular grid, and here you can see that the rank in all the cases I computed is 1, but the sort of homological degree varies, and I wasn't able to find a pattern here. However, I conjecture the following, so that these isomorphism here hold in general, and I only verified this with the computer up to 12 vertices, which is still anyway a lot. And it appears that for trees, this not homology is always 0, which is sort of weird. I find it kind of strange. Also, for the complete bipartite graph, the not homology appears to be always of rank 1 in degree 2 for all m and m, but I wasn't able to find a cycle, since these graphs tend to get quite big, and their not chain complexes even bigger, even for small values of m and n. Then also I conjecture that the cycle graph, so the triangulation of S1 with m vertices, is always of rank 1 and in degree m minus 2. Again, I wasn't able to prove this. And now, we can, however, use this not homology to prove something about the Überhomology, and let's say a sort of detection result for the Überhomology. In particular, if G is a simple and connected graph with at least 3 vertices, then the Überhomology in its maximal degree is going to be different from 0, if and only if G is the cycle graph with m vertices. And here I mean the Überhomology, not this not homology. And let me conclude with a few questions. So first of all, something I've tried a lot to look into, but couldn't find any definitive answer. We see then in the lowest degree and in the top degree, we go from combinatorial to topological information in the Überhomology. What happens in the middle? Like, what kind of information is encoded, if any, in the intermediate degrees of the Überhomology? I would really like to see an answer to this. Also, is it possible to construct some sort of specification of the Überhomology, so a topological space such that their singular or simplicial homology coincides with the Überhomology of X? And I haven't mentioned any sort of operation apart from coning and suspension that one can perform algebraically on a chain complex. Like I haven't talked about functoriality, I haven't talked about exact sequences or Cannet formula or so on for the Überhomology. That's because I couldn't establish any of these, and again it would be really interesting, especially regarding functoriality, to see what happens. For example, what is the relation between the Überhomology of a triangulation of a manifold and of its barycentric subdivision? Knowing this, in theory, could having functoriality in theory could be used to distinguish different inequivalent triangulation on a given manifold, which would be, of course, of great interest. And finally, what is the decategorification of the Überhomology? We have this triply graded homology theory. We can sort of cook two-variable polynomial as its decategorification. Does it coincide with any known polynomial invariant or combinatorial invariant of the simplicial complexes? I have no idea. Anyway, thanks for the attention, and see you next time.